section can start as normal. So reminder, there's 2 sections tomorrow, so show up there. Just pencil and yourself just to do check-in. So you don't have to have goggles necessarily. We're just going over safety protocol and explanation of syllabus. Friday, we will be having our reading questions for Chapter 1 due. We will finish Chapter 1 today, and we'll start Chapter 2. So we're all done with reading questions number 1. So here's your warning. If you have them all done and in your folder, and you just want to hand them to me at the end of today, you can. Otherwise, if you want to put them in good order, those will be due next class. And then also our second part of Chapter 1 homework will be due then. So again, we're finishing our chapter today, so you should be able to do the rest of those problems, and that will be due on Friday. And then our other big announcement is if you look at the chemistry major site, we finally have the Whitworth summer research applications are available. So those are due on Friday, February 27th. So Dr. O'Janis will be doing a biochem project, and our new analytical professor, Dr. Tao, is doing an environmental analytical project. And so those 2 professors will be soliciting for applications. So we'd love to have you apply for either of those. Yes, Clarissa.
Oh, there's been some talk about how you want the reading questions. So would you rather have them? I mean, even on the sheet that you give us, would you rather have them typed? Would you rather?
It doesn't matter. They do not have to be typed. They don't have to be pen or anything in particular. So just want the answers written out somehow. So yeah, hopefully you find even after doing the reading questions now, hopefully you might see that this could be a good tool to help you review for as you are studying for a test or something. So it should kind of be already kind of a good study guide sheet. But yeah, I'm not too worried about the format. So if it has the questions or not. So some people I see have had the questions on one page and they're writing the answers separately on a notebook page. Doesn't matter to me so much. So that part's fine. I'm not too fussy about the format.
And that was actually my second question. You said you will be turning them back to us.
Yes, you will get them back. Absolutely. Yes, you will get them back.
Thank you.
Okay, so I think we do have our last little bit actually of our reading questions. So let's actually look at one of our reading questions. And that I think is going backward to reading question number 19. So today we're going to talk about the principle of corresponding states. So the principle of corresponding states. Let's see. Shannon, do you have that one you'd like to tell me?
It is sent. Oh,
number 19 that was.
19.
Yeah, I think the other Shannon wanted to answer though. Do you have that?
Oh, I've got it. It says that real gases at the same decreased temperature and the same decreased volume have the same decreased pressure.
Okay. So real gases at the same, what did you say?
Decreased temperature and decreased volume have the same decreased pressure.
Okay, so the only thing I'm going to change is instead of the word decreased, I'm going to use the word reduced. Okay. So the word reduced here doesn't actually necessarily mean shrunken or smaller like decreased. So yes, so real gases at the same reduced temperature and volume have the same reduced pressure. So the word reduced here is officially kind of a definition that will come about in just a moment. Let's see, our second half of this question number 19 kind of said, what is the relevance of this principle? So the other Shannon, do you want to tell me that one? This can be the Shannon question.
This principle allows properties with the ranges of gases to be made into a single diagram. That's easier to look at.
Yeah, so we could say it that way. So it allows us to try and make some similarities in properties between the two of them. So 2 different gases that have corresponding variables should have similar properties. So they should somehow behave in a corresponding way. So our definitions here is that P reduced equals pressure divided by the critical pressure, and T reduced equals T divided by TC, and similarly V reduced equals V relative to VC. So the critical pressure, temperature, and volume are what we're all comparing here to. So if you remember on a PV diagram, remember we had a couple of isotherms, and then upside down we have this little inverted area that refers to where the liquid exists on there. And then we have one isotherm which just kind of skims the top of that. And it's this one special point that we're talking about here. So there is a PC, VC, and a TC associated with that point. So the P and V from our X and Y axes, the TC from the isotherm that we're on, so that defines a point. And now, relative to that, we can kind of find two gases that might correspond. So I was trying to help some people think about this on reading questions the other day. Very simplistically, I'm going to draw two graphs here. We're just going to call A and B for a moment. So I'm going to draw a little PV diagram. So maybe here I have a inverted gas liquid region that looks like this, and then maybe on my B, so I'm going to try and make my little inverted liquid area look different. Maybe I'm going to make this one shorter and broader or something like that. Excuse me. So now my point is, relative to that critical point on graph A, maybe I have a new point that I'm at point X above that up here, and I want to know what's the point X for this other gas, so what point for gas B would relate to point X for gas A. So maybe I happen to be exactly at my VC, and then maybe in terms of my temperature and my pressure, so from my PC variable, maybe I happen to be exactly twice that big. So maybe I'm at 2 PC. So on my other diagram, maybe I also have to be then exactly at VC, and whatever my PC is for that one, 2 PC would give me my point Y up there that would correspond to that. Okay, so we can say X and Y are corresponding points. And they might be completely different things. So maybe X over here, maybe that happens to be 400 Kelvin and 1 atmosphere of pressure, and maybe it happens to be 2 liters per mole. So maybe that happens to be point X. And maybe point Y happens to be something completely different. So maybe Y happens to be 250 Kelvin, and maybe the pressure is much higher. Maybe it's 40 ATM, and maybe the molar volume is 1.5 liters per mole. And you're like, well, what do those particular numbers have to do with that? What does 250 Kelvin, 40 atmospheres, and 1.5 liters, how does that correspond to that one? Well, the point is, relative to the critical point, apparently I'm at the critical volume, and I'm just exactly twice pressurized what the critical pressure was. So if that is the case, then those two gases should behave similarly. They're either both fairly real or both fairly non-ideal or whatever it might be. But in terms of their own graphs, they're in a similar position relatively, proportionately, to what that critical constant is. So they should behave in a corresponding kind of way. So if we find the pressure and take that relative to PC, and in this case, the main thing I was trying to work with is we should have a variable of 2. So in our example, PR, where I did P divided by PC, is 2PC over PC, so it's 2. So I have a reduced pressure of 2. Apparently those each have double the critical pressure. Okay? And apparently my VR, I happen to have as just VC over VC equals 1. So the reduced variable for the volume I was using as 1. I was exactly in line with the VC, and the pressure I had a variable of 2. Okay. Let's try and do that for a more realistic example with some real numbers. Okay, so as an example, argon has a temperature of 350 K and a molar volume of 0.120 liters per mole. So let's go calculate its van der Waals pressure. And then what we want to do is then go find a temperature, pressure, and volume that correspond for CO2. Okay, so we have a temperature, I have a molar volume, we'd like to calculate the van der Waals pressure, so that means using the real gas equation. And then let's go find corresponding values for carbon dioxide. Okay, so first I'm going to go find its pressure. So pressure is the nRT over V minus NV minus the A n squared over V squared. So that's just using those variables that we're going to go find. All right, so the pressure, I'll take my R, 0.08206 liters atmospheres per mole K, times our temperature, so that was 350 K. My volume on the bottom was 0.120 liters per mole. Minus our NB, so our N we don't need to have to worry about in this case, and I'm looking at my B, that is 3.22 times 10 to the minus 2 liters per mole. That's in a table. And then minus our A is 1.345 atmosphere liters squared per mole squared, and then 1 over our liter volume, 0.120 liters per mole squared. Okay, so we find an answer for our pressure of 234 atmospheres. Okay, so pretty high pressure. Okay, so now we have our T and our V and our P. Now, if I want to find corresponding values, what I have to do now is first find the reduced value, basically a factor. How many times bigger or smaller am I relative to where my critical point is? So that means we have to find our critical point. And then to kind of undo it, so like if I was starting with A, I want to find out where is X relative to my critical point. So you take all three of your variables relative to the critical point, and you're going to find a number or a ratio, like over here, 2 and 1 for the P and our V. Then you have to go from that diagram to your other diagram, what its value of PC, VC, and TC are, and then basically go up or across as necessary to find where you are on that point. Okay, so you kind of are starting at a point here, like we just found kind of a point X. We have a T and a V and a P, so I'm sort of at some X. So you have to find all that relative to your critical point, go across to some other diagram, and then kind of go up to find out where the corresponding point would be. Okay, so now it means doing some table looking up. So in a reference table, we need to go find some critical constants. So we need argon, PC, VC, and TC. Okay, so you need to look up that data point for your argon. And for argon, our PC is 48.0 atmospheres. VC is 75.3 cubic centimeters per mole. And our TC is 150.7 Kelvin. Okay, we might as well look it up for CO2 while I'm there. For CO2, the PC is 72.9 atmospheres. The VC is 94.0 cubic centimeters per mole. And the TC is 304.2 Kelvin. Okay, so now let's just go find those things. So, starting with our argon, we're going to find our reduced variables. All right, so P reduced is my P divided by the critical constant from the reference. So that is 234 atmospheres relative to 48.0 atmospheres, giving us a ratio of 4.88. So I'm almost 5 times higher. Okay, V reduced is our V divided by the V critical. 0.120 liters per mole is what we were given. And the critical one is 75.3 cubic centimeters. So I'm going to change my units. So that would be 0.0753 liters per mole to make it the same. And that would give me a ratio of about 1.59, 1.5 times bigger. And then finally our T reduced is just our T relative to TC. 350 Kelvin relative to 150.7 Kelvin gives us an answer of 2.32. Okay. So now we can translate that across again to our other diagram for our other substance. So I need a pressure 4.88 times as big, a volume 1.5 times as big, and a temperature a little bit more than twice as big as the critical ones. Okay, so now we want to find P, T, and the V that correspond. All right, so that means our pressure is going to equal the reduced pressure times its critical pressure. So now we're just multiplying them together. So 4.88 times 72.9 atmospheres equals 356 atmospheres. The volume is going to equal the volume reduced times its critical volume. So 1.59 times 94.0 cubic centimeters per mole equals 149 cubic centimeters per mole. And then our temperature. Temperature reduced times the critical temperature. And that was the 2.32 factor times 304.2 Kelvin gives me 706 Kelvin. Okay, so these would be final answers. 356 atmospheres of pressure, 149 cubic centimeters per mole, and a temperature of 706 Kelvin. Okay? Yes?
So looking at the graph, you got your critical point, and then I understand like you move up on the p-axis and across on the v, but does that mean that you're also jumping isotherms? You trying to find the 706
Right.
isotherm? Okay.
Yeah.
So you almost like move in that direction as well, like on the isotherms.
Right.
Okay.
So yeah, I kind of neglected that on my little picture there. So because really there are 3 variables and we were only plotting 2. So by picking 2 there, I was kind of already arbitrarily picking a temperature as a result that had to be on. So yes, if you were graphing that, that would turn out more properly. So I just picked 2 for easy multiples to do in class.
Okay.
But yes, that it would define which isotherm you'd have to be on as well. Okay, other questions on that example? So it's really all just taking proportions. Where are you kind of relative to the critical points? And then presumably then you could find that if one of them, again, has a certain property, the other one should as well. Okay, so I think that again brings us to the conclusion of chapter 1 reading questions and all the info that I wanted to do. So you can now hang on to those or give them to me at the end of class and we'll collect them next time. Okay, so let's move along to our next chapter. Okay, so chapter 2. We'll be talking about the first law. The main topics that we're going to be addressing here are energy, heat, and work. So interconversions of those different things. So let's see, I think we have a few definitions right off the bat with our reading questions. So let's see, let's turn to some reading questions. Let's see. Stephen, do you happen to have number 1? What is a diathermic wall? Okay, so that is a boundary that permits energy transfer. Okay, and you can even kind of look at the definition there, of course. So dia sort of implies 2, therm might imply heat or 2 different temperatures. So this is a wall that does have 2 different temperatures, maybe on either side of it. And if we were to wait long enough, apparently this is a type of barrier that would allow them to come to some thermal equilibrium later on. So a diathermic wall can enable that. It permits energy transfer between them. Okay, as opposed to, we're going to contrast that to another thing, which is an adiabatic wall. So an adiabatic system. Let's see, Cassie, do you have that for me?
It is a boundary that does not permit the transfer.
Sure, so it's the exact opposite. So this does not allow energy transfer. So this is the one, of course, that we sort of have to idealize in most cases. So most things do. We can kind of hope that they don't. But a good example might be a thermos. So if you take your hot coffee to lunch in a thermos, you might hope stays hot. In lab, we call these more Dewar flasks, D-E-W-A-R. So a Dewar flask is kind of a more professional version of a thermos. So we might hope that our hot chocolate or our hot coffee stays very hot in there. Or you can also use that for cold things. So we keep our liquid nitrogen in a Dewar, and we hope that it stays very cold in there so that the warm room temperature around it doesn't warm it and make it evaporate as it heats up. So similarly, we can try and keep hot or cold so that either way, we're trying not to allow energy transfer to occur. All right, so those are some of our walls that we might talk about. The next is, I think I have another reading question. So question number 3, what is the difference between heat and work? There's different ways that we might have energy transfer between these, and we might want to know what is the difference between them. Let's see, Jackie, do you have that for me?
Heat is energy transferred as a result of temperature difference, and work is transferred as a result of applying energy.
Okay, good. So work and heat. So she told us that work is, tell me again what you said for the work once more.
Effect as a result of applying energy.
Okay, so it's a process that we can say had energy applied to it. I might add on the addition to it that it can move an object. So you might think of like pushing a book on a table or something. You can move an object. And heat, can you tell me one more time, Jackie?
Energy transferred as a result of temperature difference.
Okay, so heat, she said, is energy transferred as a result of a temperature difference. So that kind of goes more directly along with the 2 walls we were talking about. So if I do have a diathermic boundary, I can have heat. So the process of heat is an energy transfer as a result of the temperature differential between those 2 different bodies. Let's go from there and define our total energy. So we will represent this as internal energy, which is a symbol U, so capital U. Delta U we could represent as U final minus U initial. So it is a state function. You might remember some other state functions we've talked about, like enthalpy is a state function, Gibbs free energy is a state function. So a state function means it is dependent only on those states. And in particular, that means it is not dependent on the path. So it doesn't matter how you got there, it only matters where you started and where you ended. Okay, so sometimes, as a little example, we can remember how we maybe first talked about state functions. Imagine that you and your friend both wanted to climb the mountain here, and you want to go plant your little flag on top and say you climbed Mount Whitworth or something. So maybe your friend is a great hiker and goes straight up the side and gets there. And maybe you are going to take the more slow route, and you're going to take the scenic route and all the switchbacks. And maybe, hour after they got there, you got there, and you're also going to plant your flag on top of the mountain. So you maybe took a very different path to get there. So maybe the work that you did to get there is different. But eventually, if you just planted your flag on top, we should be able to look at the altitude difference. And the delta H, if that's the function we're looking at, is the same. So you maybe took more steps to get there, but the altitude change, if that's what we're interested in, would be identical. So a state function of altitude change, height change, would also be an example like that. Okay, so just as an example of energy and units, I had a little calculation for you to do. So this one was dealing with the human heartbeat. So in a human heartbeat, so a good rule of thumb guideline is that that is about 1 joule per beat. And I wanted to know, what is the total number of calories that you consume each day that really are just keeping your heart beating overall? Let's see. Cindy, did you do that one for me?
I did. It worked out with 86,000 beats a day to be 21 kilocalories.
Okay, so tell me what you did with this factor. Can you tell me what calculations you did?
Yes. 1 joule equals 0.239 calories.
Okay, 1 joule is 1 point, what did you say?
0.239 calories.
Oh, 0.239. All right, and then what?
And then I multiplied that by the 86,400.
And where did you get that from?
I assumed it was 60 beats per minute.
Okay, so that's assuming 60 beats per minute. And then how many minutes there are in a day, probably?
Yeah, 86,400 beats in a day.
Oh, okay, so this is how many beats there are per day. Okay, and what did you get as a final answer then?
2,649.6 calories.
26,000?
20,600.
20,600 calories
Yes.
per day.
And so 21 kilocalories.
So approximately 21 kilocalories, or about 21 capital calories, the food calories. Right. Okay, so that looks great. So that's not much of your diet, right? If you eat like 2,000 calories a day. So just to keep your heart going, which is a fairly important part of your body. So you only really need about 21 calories. And in fact, that's actually also a fairly good guideline for other organs, like for one inhalation and exhalation of your lungs. It's also about 1 joule for that, so very roughly. I mean, some of them are a little bit more, like 1.1 or 0.8 or so, but it's about 1 joule per organ per each kind of time that they kind of function. So it's an interesting guideline, I thought, for especially those of you that might be interested in some medical things. So you might think, wow, well, I'm eating a lot more than that. I wonder what the rest is doing. So obviously lots of other things, muscle synapses and all kinds of other things that need to happen. Okay, so let's move along to the first law. Okay, so that brings us to the all-important first law. All right, I think we have another question here. So let's see, Cindy, can you tell me that one?
Yeah.
What is the first law?
The internal energy in isolated system is constant, so the change in U is equal to Q plus W.
Okay, good. So delta U is Q plus W. So internal energy of a system is constant. Okay, good. So she said where our lowercase q is our heat and our lowercase w is our work. So notice we do try to make a point of using lowercase variables for those. These are not state functions. So we try to reserve our uppercase letters, again, like capital H, enthalpy, is a state function. Capital U, internal energy, is a state function. But the Q and the W are not, so those are going to be path dependent. So you would have a different Q or a different W for these two different processes because they did take very different paths to get to the top. So Q and W are dependent. Okay, we have a couple of conventions. So we will use a negative side to represent something that is done by or lost by the system, and a positive sign for something that is done to or gained by our system. Okay, so when we're wondering about our Q and our W and what signs to use for those are our styles. So I have an example for that. So that was question number 6. So if we have a system losing 10 joules of heat and it also does 60 joules of work on its surroundings, what is its value of U for this process? Let's see. Katie, do you have that one for me?
Negative 70 joules.
Okay, so what did you assign for each of those things?
Since the heat was lost, that would be a negative 10 joules.
Okay.
And then the system did the work, so it would be them losing the 60 joules.
Right, so in this case, they're both leaving the system. So she got overall a negative 70. So the fact that it said we're losing 10 joules of heat, that is no longer part of the system. It apparently went to the surroundings. And it says we did 60 joules of work, so that's something we lost from that. So overall, negative 70. So this is just to give you an example of how to use those conventions. Okay. All right, so let's go look at some types of work. In particular, we're going to start with expansion work. All right, so in an expansion work, we're going to have a piston that we're examining, and we're going to assume that one wall of this is a massless, frictionless, rigid piston,